How's it going, everyone? So in this video, we're going to cover the basic theory of Chapter 9 and work an initial example before the second video where we'll actually do part of the example problem that's on your exam 3. So really the theory of Chapter 9 is about centers of gravities, centers of mass, and centroids. And what is a center of gravity? Well, think back about all of the free body diagrams that we've drawn of bodies so far in this class. In the vast majority of scenarios, very rarely have we actually neglected the mass. So as long as we were considering the mass of that body, we've always drawn in our free body diagrams a weight vector. And it's very easy to actually compute the magnitude of that weight vector, particularly if we're near the surface of the Earth and we can model the acceleration due to gravity as constant. It's simply m times g, where the value of g obviously depends upon the unit system that you're in. In addition, we've never had a question about the direction with which we should draw the weight vector. It's always in the downward minus y direction, which is assumed to point towards the center of the Earth. However, one thing that we haven't talked much about is where we actually put that vector. And we know when we're actually dealing with problems that can't be modeled as particles, that the location that a force is applied really matters with respect to influencing how it tends to rotate. Up until now, sometimes we've had a body in 2 dimensions that I've said something like, oh, if you can draw 2 lines of symmetry, put the weight right at the intersection of those 2 lines. Or sometimes the book is kind enough to put a dot on the actual diagram and put a G next to it. And we've said, oh, this is probably where we should draw the weight. And in both of those cases, what we're doing is we're trying to approximate or identify what's known as the center of gravity. So what actually is the center of gravity? Well, when you think about any body, we're talking about its weight as a single number. But really that body is composed of matter or mass that's distributed in space. And every small chunk of that body has a mass associated with it. So really, weight is not a single concentrated force. It's a distributive force. So what we're doing when we model it by a single force is we're representing that distributed weight as a single equivalent concentrated force system. And that's something that we've done a lot in the course up until now, particularly dealing with distributed loads on beams. And we know that in order to represent a distributed load as a single concentrated load model, we need to do two things. The first is to determine the magnitude of that vector. And remember that the way we did that is we simply added up all of the distributed force in that case, and we made that equal to the actual magnitude of the concentrated force. That adding the majority of the time when that we had a continuous distribution was accomplished through integration. Because remember that integration is nothing more than summing up a quantity with infinitesimally thin slices. That's the whole idea of the Riemann sum that if you remember back to your calculus class was how the idea of a definite integral was derived. In addition to needing to determine the magnitude of that equivalent single force vector, we needed to determine where to actually put it along the body. And in all those cases, we've basically up until now just looked at a table. But think back to the case when you had a uniformly distributed load. It went right in the middle. That's because you had a little bit of symmetry to it. Now think about the case when you had that linear load that corresponds to a triangular distribution. In that case, it went 1/3 of the way from the peak edge of the actual load, or the kind of higher height end of the triangle. How did we come up with those numbers? How did they actually get them in the book? Well, the way that they got them is they basically determined a location such that if you put the single concentrated load there, the rotational effect of that on the body would be the same as the equivalent distributed effect of all of the little distributed loads. Now, that's really hard to kind of understand when I'm saying it in terms of words, but let's look at a diagram on the next slide and it'll make a little bit more sense. So say you had some body as is shown here in blue, and you were to chunk it up into all these little infinitesimal chunks. Each of them would have some weight, call it dW. Now you could represent the weight of this object as the sum or the kind of the concatenation, for lack of a better term, the combination of all those small little weights of the objects. However, from a modeling point of view, it's going to be so much easier if we can just represent that as a single equivalent force. So what do we need to do? Well, this single equivalent force, which corresponds to the weight, will pick the magnitude to be equal to the sum of the weight of all these little chunks. And since these are infinitesimally small, we'll do that by integration. In addition, we're going to put this in a place such that if we were to compute the tendency of this single force to induce rotation about, say, the x-axis, in that case, what is the tendency of this single force to induce rotation about the x-axis? Well, the perpendicular distance from the x-axis is y bar. So I can easily compute y bar times w, and that's going to give me the tendency or the moment of that single force about the x-axis. Well, could I not do the same thing for the moment about the x-axis of each of these little individual chunks? And what would happen if I added them up? And again, the adding up is going to come through integration. what I would be doing is ensuring that this single equivalent concentrated force system induces the same moment about each of the axes as the distributed actual real force system. So that's all these three equations are doing, is it's basically saying I have to pick the location at which I apply the single equivalent force, which is denoted by x bar, y bar, and z bar. So those are notation that you traditionally use for the center of gravity. I'm picking those in such a way that the rotational tendencies about the axes for both the concentrated load system and the distributed load system are the same. So let's talk a little bit about center of mass as opposed to center of gravity. So remember that in the simplistic modeling that we do, where we're considering bodies close to the surface of the Earth, where we can actually model the acceleration due to gravity as being constant, that weight is simply proportional to mass. So in addition to talking about a center of gravity, I could also talk about a center of mass. And the approach would look quite similar, only rather than actually talking about the force weight being distributed, I could talk about the mass being distributed. In that case, of course, it will no longer be a vector, but from an actual equation point of view, if I just substituted in W for M, that would be the same ideal. And again, the only difference is that they wouldn't be vectors there because they're just chunks of scalar quantities known as mass. Well, think about, can I not do that for little chunks of volume, or in a two-dimensional case, little chunks of area as well? I certainly could. So in the case that maybe, and that's what we're going to be considering in this particular chapter, if you have just a two-dimensional area and you assume it's actually it's homogeneous, so the density across the area is uniform, in that specific case, the centroid, or the kind of geometric center of the shape, is going to be the same as the center of mass. It's going to be the same as the center of gravity. So whenever you have an actual object in front of you and the density is relatively homogeneous across it, you can kind of identify where the center of the centroid of the object is just based upon its center of gravity. And the way I always think about the center of gravity is, if I have an object, where would I put a single finger underneath in order to balance it? So imagine that this pen was perfectly symmetrical along its axis. It's not, right? It kind of tapers thinly down here. We have this holder here as well. But if it were perfectly similar, I could put a single finger underneath right in the middle and it would balance. So that same idea applies to something like an actual piece of paper that's relatively homogeneous. Imagine it were rigid. I could just put a single finger underneath at the intersection of those lines of symmetry, and it would balance the paper. So that's getting the idea that the centroid of that area is the same as the center of gravity under those limiting conditions. So let's actually talk about how we would actually solve these equations, and imagine that we just swapped in an A for a W. So we're going to be talking about centroids, or geometric centers of area. So they're still going to be denoted by X bar and Y bar. Those bars over top are telling us that we want the centroid. Well, how would we actually do it here? Well, if I go back to these equations and I just swap in a W for A, let's look at how they would look. If I wanted to determine the centroid along the x-axis, or X bar, all that I would do is I'd find the total area, and I would use that to divide by the integral of I'm breaking that little area into chunks, and I'm going to take the infinitesimal area of each little chunk and multiply by the actual distance of that chunk from the y-axis in this case. So it's easier to see with an actual example here. So the one that I'm going to give you on the test, a little bit of fair warning, and I will set it up for you, is not going to be an area where the curve y is bound as a function of x. It's going to be a curve where x is bound as a function of y. But anytime you have the y value of the bounding curve expressed as a function of x, what you want to do is cut that area that you're trying to find the centroid of into little rectangular chunks. Now, why would you want to do that? Well, if you cut this into a little rectangular chunk and you allow the width of it to become infinitesimally thin, so that's going to be actually your integral element dx. What is the area of this little infinitesimal chunk? Well, we'll denote it as d, just because it's going to be going to 0 as dx goes to 0. But the actual height of this rectangle, remember that for a rectangle, the area is always the width times the height. So the width is dx, the height is going to be y. And if we have y as a function of x, what is going to happen is this infinitesimal area element, dA, is going to be something that we know how to integrate using only single variable integration. So in this case, dA, it's always y times dx, but if I can express y as a function of x is x cubed, then dA becomes x cubed dx. So how would I actually go about trying to determine what the centroids of these little areas are? Because that's going to be important in the actual integration as well. Well, if you think about this little rectangle, we know that for simplistic shapes, basically the centroid is always going to be right in the middle. So for this little infinitesimal area, the centroid of the area in x is just going to be x, And in y, it's going to be y over 2. So wherever I move this little dA to, its centroid is going to be x variable distance from the y-axis, and it's going to be y over 2 units up. But remember, I want to work in a single variable here, so I'll express y over 2 in terms of the relationship between y and x. Since y is equal to x cubed, y over 2 will just be x cubed over 2. So now it's really just a matter of doing some calculus here, right? All that they've done is they've taken these equations here, replaced the w's with a, and they've solved them. And remember, this is a two-dimensional problem, so they've solved them for x bar and y bar. So what this says is I can compute the centroid in x if I, in the denominator, have the integral of the entire distributed area, which we know how to do because remember we have dA in terms of x cubed dx, so that's just a single variable integral, going to be a power rule. And in the numerator, right, all that I'm doing here is actually determining what's known as the first moment of that area. And is this something that we actually can compute? Well, yeah, because x tilde is nothing more than the centroid of the infinitesimal area. Remember, all these little rectangles have a centroid of x, just wherever you're at along the x-axis. And dA, we already mentioned earlier that that's simply going to be equal to x cubed dx. So generally speaking, this is a characteristic that happens a lot in the actual integrals that you're taking, where you'll have just one additional factor of x in the numerator. And again, that's because this is called the first moment of that area. So if you just compute both of these integrals, both are simply power rules. In the denominator, you have x cubed. In the numerator, you have x to the fourth. Remember that whenever you're taking the antiderivative of a power function, what you need to do is increase the exponent by 1 and divide by that new exponent. So x to the fourth, its antiderivative becomes x to the fifth divided by 5. X to the third, its antiderivative becomes x to the fourth divided by 4. Both of these we're evaluating over the integration interval. Now, why is that integration interval from 0 to 1? Well, notice that the actual area that we're trying to find the centroid of, it has an x value that ranges from 0 to 1. So that's what I'm integrating over in this case. And just follow through with your integration, and you'll find that the centroid x bar is 0.8. If we do a similar thing for y bar, remember that in the denominator, that's simply the total area of that shape. So it will stay the same. We don't need to recompute it. It's still 1/4. And what we're doing in the numerator is we're summing all of the individual centroids of that with respect to basically the x-axis. So basically, you can think about this as if you were to have this parabolic area and you were to apply a particular weight vector corresponding to that centroid, where you would put it is going to basically, that last equation is making sure that where you put it in y is going to enforce rotational equivalency about the x-axis. But if you don't want to think about that and you just want to do the math here, y bar, again, is the actual centroid of the little infinitesimal area. It's y over 2, but to do the integral, we need to express y over 2 in terms of x. And even though this looks relatively complicated, if you just follow through with your integration, it's just a power rule integration, and you eventually would get 0.2857. Now let's think about if we can kind of test intuitively that those centroids ended up where we thought they would be. So if in the case of, even though centroids are kind of independent of the ideal of center of gravity, just think about that as being a uniform distributed thin plate. Where would you actually put the balancing point at? Well, the majority of the area is over here towards the end of the plate in x. And remember that this is 1 meter long. So it's not going to be surprising that the centroid in x is going to be near 1. In addition, the majority of the area is actually concentrated near the x-axis. So it's not going to be surprising that the centroid in y is going to be near 0. So I would expect a centroid, if you were going to try to balance this, as being near 1 in x and near 0 in y. And if you notice, that's exactly what we've determined. In x, it is 0.8, and in y, it is 0.2857. So that is kind of my best attempt to give you a physical explanation of what's going on. To some extent, though, you can just treat it as a simplistic calculus problem. And hopefully through doing the actual example on the exam, it'll be a little bit eye-opening to you of how to set it up. I'm going to record a separate video on that. I'm going to set you up for determining the x and y centroid. I'll actually work through determining the whole x centroid. Then you just have to finish it up for the y. So I will see you all in the next video.